Well, hello, everybody. Welcome to this Green Energy series. Good morning. Welcome, solar aficionados, to this wonderful event. Today's event is we're going to get a presentation about a unique solar PV system that has integrated thermal capture as well. And we'll be hearing from a presenter named Doug, and we'll introduce him shortly. We'll go to the next slide. Before we begin, let's do a plug on Solar Oregon. Solar Oregon is a 501c3 nonprofit that has worked to encourage solar and storage adoption throughout Oregon. And Solar Oregon has been around for 43 years. So Solar Oregon's main activities are to provide reliable and impartial consumer education. Solar Oregon also works to build the clean energy community and perform outreach and some policy advocacy work. We host events such as How to Go Solar plus Storage webinars. We also do solar tours. We also organize solarized campaigns, and we do peer-to-peer education events such as this one. If you like the stuff we do, we encourage you to donate and or become a Solar Oregon member. We're a lean organization with only 2 staff. Everyone else graciously donates their time and energy to this important cause of educating the public about solar and storage and encouraging others to adopt solar and storage. Next slide. So one of the upcoming events is another How to Go Solar plus Storage event webinar. It's a free webinar. It'll take place August 1st. If you have friends or family that are interested in learning more about how to go solar, this is a very good intro webinar. It's kind of like a solar plus storage 101. So please share this event. You can find it on Eventbrite. We can also send you a link if you want a direct link to be able to register for this event. And then look around on your screen. You'll find Zoom controls for how to enter your questions into the Q&A. We encourage you to use this feature to submit your questions throughout the presentation. Next slide. So today's speaker is Doug, and he's a retired solar professional. He built his first solar house 50 years ago in 1974. Man, hard to believe that solar was around back then already, but indeed solar has had beginnings as far back as 1974. And even then, that was not the first beginning of solar. Doug started his solar research and consulting career at Portland General Electric, 20 years. And then he formed his own consulting business, Cascade Solar Consulting, in 1998. After Cascade Solar, he worked several years as a commercial solar manager at Energy Trust of Oregon, and he retired in 2012. In 2009, he built his second home in Happy Valley. And we'll get to hear about his solar system that he installed in this home. So without further, we'll keep going.
All right. Thank you very much, Edward, for that introduction. Yes, it's been a while, and I was counting the years, realizing that this year was 2024, and we built our first solar house in 74. That it had been 50 years. It was a shock to my system as well. Well,
are those original panels still working?
Well, that original house built in 1974 had 20 solar thermal water heating panels on it. And after the first 20 years, the roof that was underneath those solar panels started leaking. And unfortunately, we had to remove them, but we put our first photovoltaic system on that first house. in the early 1990s, 1992, and did my own homebrew solar photovoltaic system, my own wiring harnesses and everything. And it was great fun.
Well, that's very encouraging to hear that the solar panels in the original house outlasted the roof.
Yes. Oh, they would have gone longer if it weren't for the roof. And those were solar thermal. And then the photovoltaic modules that we've had since then, of course, have just go on forever. They just never quit. So,
Yeah.
but when time came for us to move from that house, and decided we wanted to build a new house, that we incorporated all the things that I had done wrong with the first one and add in some new features. And one of them in our new house built in 2009 here at Happy Valley was a combined photovoltaic and thermal system. And so now that we've got 15 years using the system, we can share some of the things we've learned. But first of all, let's just talk about what are photovoltaic thermal systems, or PVT as they're sometimes called. Well, these are systems that from the same racking and mechanical setup, you capture photovoltaic electric energy and the thermal or heat energy that gathers up on those photovoltaic modules. And you take that energy, the heat energy, and you direct that to some other loads where you might want to use hot water. This picture here happens to be a system set up at a high school in Vancouver that was back in 2010, a year after we had put that on our house. And this does take the heat off the back of the photovoltaic modules and also provides fresh air for the building at the same time. I won't be talking about that one. All right, why would you want to combine a photovoltaic module system and then capture heat off of that? Well, first item, it saves the cost of two separate systems if you want to do solar water heating, for example, and then get electricity as well. Back in 2009, the cost of solar photovoltaic systems was quite high. And so anything that you could do to increase the energy output of a photovoltaic system would improve your economics. In addition to saving the cost of two separate systems, whenever you are able to cool off or take the heat off of a photovoltaic module, you improve the efficiency of that photovoltaic module at the same time. So that there was a win there. You could increase efficiency 0.5% per degree C that you lower the temperature of that photovoltaic module. And also, if you have a limited roof area, you don't have room for both a photovoltaic and a thermal system, you can combine those two outputs together in the same system. And so that's the reasoning behind the two. Well, what do you do with this excess heat that you can take off the system? Well, generally it's domestic water heating. You preheat hot water, provide supplemental space heating, make up air tempering, and I'll explain why all this works this way and we get into the actual system that I use. Night radiation cooling, which would be nice on some of these hot days, and potential other uses. Warm air, using the warm air that comes off them for drying clothes, or even fruit drying if you're into that. Well, okay, let's describe what a PVT collector system would look like. Typically, the systems that were available 15 years ago, you had a photovoltaic or an array of photovoltaic modules. And then in addition to that, you had a second stage, which was a metal collector with a glass cover, a glazed collector. So you would bring ambient air or outside air underneath the back of the photovoltaic modules. It would sweep up behind the back of the photovoltaic modules, picking up heat. And then that air would continue to go up through the glazed collector follower, and that would be boosted up in temperature. And then that warmer air would be diverted then down into where you need it for heating water or whatever, and we'll show that in a minute as well. So you have the photovoltaic modules and the framing system. You create a ductwork out of the framing system, and then put the glass collector up at the top and adds on to that. Here's the whole system. This happens to be a particular brand that was available back 15 years ago called Echo Solar. And this little diagram shows where we have the array. The air comes in from the outside. It comes through a ducted system and it blows across an air to water coil. And that water is circulating from a preheating tank. This is what you want to preheat your hot water for your domestic uses. So that warm airstream heats up the water all the time while that system is working, preheating the water. Now, if you can't use that hot air, then it automatically exhausts all that remaining hot air to the outside of the building, gets rid of it, takes it away from the photovoltaic modules. And so this is kind of the basic system diagram.
So Doug, in that last diagram, is there a glazed section and a PV section?
The glaze section and the PV section are really all together. And I'll show that in just a minute when we show the actual pictures of the construction of the system on my house.
Okay.
So this is our home with the Echo Solar system is 2009. The original photovoltaic system was 4.7 kilowatts. And here you see the cost here, about $6 a watt. The PVT add-on was the amount shown, 10,000, for another $2 per watt. And if we look at this graph showing the cost of solar back in 2008, 2009, the cost of photovoltaic systems on residential, this is residential system cost, was around $8 per watt. Of course, thankfully, we had lots of solar incentives back in those days, so the cost ended up being probably a little bit around half of that, the cost that I show here. So this system was fully operational from 2009 to 2018, and then I say it was uncontrolled 2018 to now, and I'll explain that in a minute. Now you can see the pictures of the house. It has notably greened itself over those 15 years with our trees and vegetation. That's very nice. The system on our home was an off-the-shelf system. Again, the brand name was Echo Solar. That particular system partnered with a home builder in Arizona, and they put on a whole bunch of these Echo Solar PVT systems on those homes in Arizona. Well, then in 2014, Echo Solar was sold off to SunEdison, big purveyor of solar systems at the time. And then in 2019 or 2018 sometime, they went out of business. This Echo Solar, the whole set of features that went with the Echo Solar system, just quit. And I'll explain what impact that had on us in just a minute. Okay, the photovoltaic, the PVT system at our house. Again, the PVT framing system ducts through the roof. It's called an energy transfer module, where the fans and the pumps are located. And then including the portable water heating system and the control system. And so here are some photographs of that system under construction. So this is the initial picture of the roof with an ice and water shield on the on the roof itself. And then on the left side picture, it shows they laid an aluminum metal roof on top of the ice and water shield roof. So a complete metal roof is sitting on that. And then embedded into that metal roof, there are these scoops that will draw in air from underneath the photovoltaic system underneath the whole system. And so you can see the scoops there at the top, and then underneath the roof, well, we're taking this warm air from behind those photovoltaic modules and we're bringing them through a ducted system. Insulated ducts, as you can see on the underside of the roof. Here's another picture showing the scoops that through which the preheated air goes underneath the photovoltaic modules. All right, this is the photovoltaic array. This is 7 modules, 7 225 watt modules in each row, and there's 3 rows of them for 21 modules, 4.7 kilowatts. And then on top of that, this is without the glazed follower, this picture. So this is just the photovoltaic modules before the glazed follower has been installed. And then this is the system as it was completed. The rows of photovoltaic modules, the glass covered thermal booster module at the top, and then the scoops collecting the warm air underneath. The picture on the right here is this energy transfer module, as they call it. It's where all that warm air that comes from behind the photovoltaic modules goes into this and again blows across an air to water heat exchanger, and where that's transferred into hot water, the hot water stream, and then the remaining air goes into is exhausted. Or we had a feature of this system where you could help warm your house with air from the system. So I'll show that in a minute. This is the controller on the left we have, and then this is our water preheating tank that is accepting the warmed water coming down from the PVT system, and then this is our backup instantaneous gas water heater. All right. Well, I'm an engineer. I'm a data nut, I guess. I want to see how everything works. I'm an experimenter, which is why we tried the system in the first place. Let's see how it works. Well, thankfully, initially there was a system that came with the PVT system. It was a really nice interface that provided all kinds of data, and so I started processing that back in 2010 after we had moved into the house. And here are some of the screens that we were able to, information we were able to get in real time. We could log into the system. One of the good points and one of the bad
from
points.
2010.
Yeah, this is 2010. This is a screenshot taken in 2010. One of the good and bad points is that it had a nice interface up on the web, and so all the data from my house could be transferred up to the web and put on all kinds of graphs, charts, and pictures. This was an interactive and cartoonish. Whenever energy was flowing, all the things would be animated and show where hot water was being collected or warm air was being collected for heating the house. The instantaneous output of both electricity and thermal energy were all measured, all the temperatures. And so this is really nice to have this kind of interface. And then we could also control what's going on. Now, one of the features of this system that I hadn't mentioned before was we could draw that warm air off the back of the photovoltaic modules. And when the conditions are right, typically in spring and in fall, when we wanted to help heat the house, we could pull that airstream into the house and it would boost the temperature in the house, and we could back off on our heating system. So we could control which temperatures we got off that system and could pull into the house. And that was quite useful. This other feature says solar home cooling. Another interesting feature of this system is at night when the photovoltaic modules are in the night air, and also if it's a clear night, those photovoltaic modules temperature will actually drop to below the outdoor air temperature. It's called night radiation cooling. And so there was a feature that we could operate wherein we could pull outdoor ambient air underneath the photovoltaic modules at night. That airstream would cool off, and then we could pull that cool airstream into the house for night cooling, to enhance night cooling. And at the same time, of course, that brings in fresh air into the house. So it was a nice feature, especially in the summertime. We do have lots of windows in the house, so we can open them up to cool things down. But for a number of times, we were able to experience cooling from the backside of those modules at night. Anyway, this interface was really nice. We control all these things and get more energy off the system, or use the system to get rid of energy we didn't want to have. One of the screens that we could get is an annual. This is from calendar year 2010, at least through October. And this shows the green bar is total energy provided by the PVT system. The magenta bar was all the photovoltaic electrical energy from the photovoltaic part of it. The yellow was energy that came from the system that was used to help heat the house. And then orange is energy from the system used to help heat water, for domestic water heating. You can see that in the spring months, we were able to get a fair amount of supplementary heating for the house for that. Excuse me, although for the domestic water heating system, contributions to that actually picked up in the summertime when we were really able to get those higher temperatures. So this showed, for example, that period of time between January and October 2010. There's a reason why I only have these screenshots from 2010. And I'll show you a few other things first. We could collect the data in very fine packets. For example, this is a series of days in October of 2010. The red is the temperature in the photovoltaic modules. The orange is the temperature in the water heating, domestic water heating tank. And you can see after a series of sunny days, defined by the peaks here, the temperature in the water heating tank kept kind of stepping its way up. And of course, after a series of cloudy days, we'd be using hot water, and the temperature of the tank, of course, would go down. This is in October. Temperature in the tanks was around 100 degrees. And if we wanted to really be busy, we could see the data happening, temperature data happening throughout the system. The temperature from behind the modules, the temperature in the water heating tank, the temperature supplied to the house for that. It even had an outdoor temperature sensor. You can see that's the gray line down. So we knew what the temperature fluctuations were happening on the outside as well. It was a robust and highly entertaining interface with the system. A couple of samples of data for water heating. And this is the typical winter, spring, a series of sunny days as seen by these blue peaks here. That was the temperature at the tank bottom of our preheating tank. And then orange is the temperature at the top of the tank. And we would get that level of definition. Here's a series of sunny days happening in the summer where the temperature, the first sunny day of the series picked up the temperature significantly, and then it just kept getting higher and higher. And eventually, sunny days gave up, and then we would go from there. But that's temperatures up around 100 degrees are pretty typical for summertime. But because we have our water heating set at 120 degrees, we still have to use some backup energy for water heating in the summer months. But let's show you the results of what energy we were able to get for water heating off this photovoltaic thermal system. This is the last 11 years of natural gas bills. The only thing we use natural gas for in our house is for the tankless gas water heater. So anything that I mean, you can see how this is therms per month that I actually had to do a hand reading at the end of each month to get this data for all these years. You can see it goes down significantly in the summer months, which shows that the PVT system is working for us. And here's what we estimated the savings to be. In the dead of winter, we use about 5 therms per month for water heating. I assume that we would use 5 therms per month every month of the year, except for a little downturn in summer, perhaps because of warmer incoming temperatures. But nevertheless, around 5 therms per month. And that anything less than 5 therms per month has been provided from the PVT system on that water heating, preheating feature. So doing the calculations, we would expect to use around 1,800 kilowatt hours. I'm converting therms to kilowatt hours here, equivalents. Around 1,800 kilowatt hours for water heating. We actually use about 30 therms per year, or about 900 kilowatt hours. So my estimate is that the PVT system, the output of that goes to water heating, is about 900 kilowatt hours worth of thermal energy. That's pretty good. I like that. That provides for me what I kind of expect from a solar system, is about a 50% savings. Well, counterbalancing some of that savings, there is a fan that comes on whenever we're drawing air from behind those photovoltaic modules. And so there's a little price to pay for the energy that we get off of that system. And I figured that that's about 250 kilowatt hours of fan energy per year. This is just an aside. I use a monitoring system called the E-Gauge monitoring system, and I'm able to, off of 16 circuits, I'm able to measure everything that goes on electrically in my house. And this, you can see the green is energy that's been provided by solar from the photovoltaic system. And then the red is energy being used by the house. This is just a screenshot from last week, or third week in June, actually, just to show what it might look like. So we also get data off this E-Gauge monitoring system, and that's why we're able to provide information that we have. Well, early on, we did some studies trying to calculate how much energy was provided by the PVT system. This is for space heating. Okay, I've been talking about water heating as one of the benefits. This is for space heating. In other words, energy that was collected from behind the photovoltaic modules and then blown directly into the house for helping to heat the house. In these first 4 years, where we had good data coming in from all of our data sources, about 4 to 6% of the energy we needed to heat the house was provided by the PVT system. The rest of the energy that our house uses for heating, we have a large passive solar south windows. And these are the actual calculations indicating how much we collect from our south windows, how much our heat pump system extracts from outdoor air, and then how much the heat pump system actually uses in energy from the utility company. So, which is only like 20% of the space heating needs of the house is supplied by buying electricity from PGE, for example. That was the first 4 years, and the reason why we have just those 4 years of data at this detail is because in 2014 to 2018, SunEdison took over the system, and then trying to get data off of and to use the interface to the photovoltaic thermal, the PVT system, started failing. We could not get into the website. We could not control the space heating feature and the night cooling feature. And to us, that was a loss. And that's why we haven't got any really good data other than the savings in water heating that we're able to get from our natural gas bills, that we've been able to discern what we actually get. So what are the issues? This is about lessons learned. Let's see what lessons we learned. The excess thermal energy, which frequently occurs in the summer months. Do we get the most when we need it the least? Well, what about the fan and pump power? Are the benefits that we get from the system worth the energy that we use for those two uses? And the efficiency of photovoltaic modules as thermal air collectors, is that high enough to be beneficial? And how do we really calculate the costs and benefits? These are all issues. Interestingly, back in 2010, which was the year after we have the system installed in our house, there was a study done by some scientists in Albuquerque, New Mexico, of the photovoltaic system, particularly the brand name that we actually purchased. And they reported on this study, the detailed data and all this, in May of 2010, the year after we installed the system. And these are the conclusions, interestingly, and I found this study actually a number of years after 2010. But here's the conclusions that they reached. For an air-based system, photovoltaic modules, trying to use them as a thermal collector, the efficiencies are low because there's no additional glass cover that keeps the heat on the photovoltaic modules. And in fact, you want the modules to actually lose heat. The space heating contribution, they said in their study, was typically small, 4 to 6%. And indeed, my data confirms that that's the range of space heating help. It's not inconsequential. In our case, it was almost 700 kilowatt hours worth of heat per year, but still relatively small. What they did find is that the photovoltaic efficiency on an annual basis produced enough additional output that it actually paid for the energy used by the fan system. So you do get improved efficiency from the photovoltaic system, and the fan power, they kind of cancel each other out, so to speak. But what that does mean is that the additional energy, the heat, the thermal energy you get off the system is all profit, is all thermal profit. So, so yes. The thermal collector fall with that additional collector that has the glass cover does help achieve the temperatures necessary for water heating. So that's a good thing, and I'm pretty sure that has helped my system get up to that 100-degree range in the most of the summer months. But you have to reject most of that summer heat because it's just too much. Kind of go through the last two. Okay. For us, for our household, the PVT system works adequately. The initial cost of the system at $8 per watt installed was about the same range as all photovoltaic systems at the time in 2009. We were able to take advantage. We did have a limited south roof area, and we tried to jump through a lot of hoops to try and find where we would put a solar water heater and a photovoltaic system on that south roof. And this actually solved that problem for us. The fact that we're able to get 50% of our water heating from the same system as the photovoltaics was great. And we covered the roof with the photovoltaics pretty much. So the water heating that we get, 900 kilowatt hour equivalent per year, increase the production of that initial photovoltaic array that was part of the the PVT system. That was the 4.7 kilowatt original system on our house. Produced about 4,500 kilowatt hours worth of electrical energy and 900 kilowatt hours of water heating. So it increased the performance of that roof by 20%. I think that's good. The fan energy that we used, that's acceptable to us, especially if it's considered that it offsets the improved efficiency of the photovoltaic modules. They get better, but takes a little energy from the fan to get that, and that's fine. We would have gotten a lot more benefits over these 15 years if the EcoSolar, which became SunEdison, if that whole chain of manufacturing had and support had not collapsed in the mid 2010s. We were not able to take advantage of the additional features because we couldn't switch between, we couldn't turn on the space heating feature or the night cooling feature because we lost control, because we lost that interface, completely dropped off the web, dropped off the internet. So I guess that's a caution that think about orphaned systems. If you have a system that, especially the interfaces in the web, what I kept hoping for, and I was unsuccessful after numerous attempts, was to find a way that I could control all these features locally through a local control system, and it just didn't. I wasn't able to do that. Everything just kind of fell apart in 2018. Well, how would you improve a PVT system? Well, I'd say if you have a house with a larger space heating bill or larger water heating bills, you capture more energy, more useful energy from that system. Our house is a LEED platinum house, so it's space heating. It's very tight, very, very efficient to begin with. A steeper roof that faces more towards the winter, so it would collect more winter energy for space heating and water heating, would be another improvement. Add uses of that excess hot air. Now, I had toyed with the idea of somehow hooking up a clothes rack at the output of the exhaust of that system, and the temperatures would be just about right, just about 100 degrees. It's a very dry air that comes off of that. And so clothes drying was a thought if you have a setup that you can do that. I'm also toyed with solar food and fruit drying in my house, and the temperatures coming off the system would be about right for that also. So, some other ways might be able to get more out of this kind of system. Or, and this is kind of my throwaway line here, is just add on more photovoltaic modules at the prices today, significantly less than what I paid in 2009, and get a heat pump water heater and put the two together and see how that works. I'm going to turn this back over to Edward in just a minute, but I thought I might show. This is our house. We originally built the house with a 4.7 kilowatt photovoltaic system. And that was all, the PVT system was all part of that. So the first few years, we were getting about 4,000 plus kilowatt hours off of that system. And then in 2013, and actually in 2014, I added another 3,400 watts on our garage roof. So we have a total of an 8.1 kilowatt system on our house. And what's interesting about this graph is over the last 10 years, how stable the output is from that 8.1 kilowatt photovoltaic system that we have. The predictions are just spot on for almost every year. Okay, that's all I have to chat about with the PVT system, and we'll turn it back over to Edward.
Sure. Before we turn it back to me, there's some questions. One of which is about maintenance with this system. Can you comment on maintenance?
Sure. I'm trying to think of what I have done to maintain the system.
Did you need to clean the ducts, clean any air filters? Did
Well,
screws get inside those
okay,
ducts?
let's see. The ducts are unreachable. They're up in an
brilliant.
attic, and they're buried in insulation, so to speak. The filter, there is one filter that I've looked at, and I just looked at it last year, and it looked pretty clean. I didn't really do anything with it. The little pump that circulates the water from the preheating tank to the PVT system, the energy transfer module, as they call it. Haven't had to do anything with that. Really, there's been no maintenance on it.
Okay. Can you comment on the tax credits that you were able to get back in 2009 when?
Oh, I have to structure that together. You know, the total system cost was like $39,000. And I think we ended up paying about 15 to 20,000. There was the federal tax credit and the Energy Trust rebate were all available back then, and they were pretty substantial. So it was around 50% of the system cost. Now, the total cost of the construction of the house was about 500,000. So we spent a net about 20,000 out of 500,000, and that's about if I do the math, it's what, 5%? Yeah, 5% of, and what I like about it is it's going to provide energy for the house for the next 50 years, long after I'm gone. And so we're buying energy in advance, and we're also getting the additional value on the house that if you're able to sell a house that says, oh yeah, by the way, electricity is free, which is it's a good selling point and it enhances the value of the house.
Okay. Have you tracked the advancements in PVT panels? Are there particular ones on the market that are an improvement to the one you have? Any thoughts on that?
You know, I have not tracked that, and I'd say one of the reasons I have not tracked that. Well, I mean, I jump in every once in a while and dial in PVT and do a search, and all I find is historic information about the old system that I have. And I think what happened is that when photovoltaic systems dropped from $8 a watt down to $2 to $3 per watt, people were scratching their heads and saying, wait a minute, why do we need to have a separate thermal? So we'll just apply buy more photovoltaic modules at that cheap price and power
Heat
a
pumps.
water heater with that.
Yeah.
So no, I didn't pursue it for that reason, is that it didn't look like there was other people interested in it.
Yeah, so Doug, I've put in the chat a few links to some companies that still make hybrid PVT panels.
Yes,
And so for anyone interested, I assure you that none of those are good bang for the buck compared to how cheap solar panels are nowadays. So I think, Doug, you are correct that pure solar panels have gotten so cheap that it's just better to install more of those and run a heat pump than try to get the thermal out of it. But in places that are extremely hot, maybe like think Phoenix, Arizona, for example, it could possibly be for longevity's sake or whatnot to have some sort of liquid cooling of the panels. But then again, like Dubai, they get extremely hot in Dubai, and they have whole entire commercial utility scale solar farms, and they're not cooled at all. So they just accept that they have a um, efficiency loss during certain temperature periods.
right. I think that you're right. The prices, the dropped prices just make it, yeah, unnecessary to try and get additional energy off of those. So,
Yeah. So, and then there's also a link for a SAHP. It's a UK based company, and they do just thermal collectors that connect to a heat pump with the idea that you get the radiative heat collected off those black panels that have refrigerant running for them would be added to the air, the convective heat that's captured through the standard air source heat pump, so that you can get better extreme cold climate performances off of a heat pump than just a straight air source heat pump.
yes, I have read about the solar assisted heat pump, as
Yeah, exactly.
in
Exactly.
Britain. Yeah,
So it's an interesting
yeah.
concept. I have no idea how well or not well it works.
If you take the preheated air off the back of the modules in wintertime, you'll warm it up and then improve the performance of an air
Right.
source heat pump. Sure. Yeah, yeah.
Exactly.
I think that would work.
Um, there's another if you fill your roof with PV, why not also try to take off the thermal? So have you ever thought about removing your old panels that are the hybrid panels and just installing more PV there? Would you get better performance?
I'm sorry, taking off the thermal
Your
followers.
exactly. Taking off your PVT panels and installing modern day just straight PV panels.
PV. That's an intriguing thought. I have space for there's seven modules wide by one row that are all the thermal follower modules that yeah, could be replaced by PV. See, we could put 7 times 250 watts, another 1500 watts of photovoltaic modules could go up where we have the thermal followers.
Yeah, but I mean, is there any
That's a thought.
the PV stuff like has the efficiency of the PV panels themselves, like from 2009 versus 2024, have the efficiency of the panels gotten so much better that you would want to replace the panels also?
So I've taken data every year from the photovoltaic system. That's data that I've been able to get consistently. I've not noticed in those 15 years any decrease in the performance. At least it's not noticeable. On a sunny day, we're still, getting roughly 6 kilowatts peak on that sunny day. The amount of energy that's produced around the solstice in the summertime is about, on a bright sunny day, is 50 kilowatt hours per day. That really hasn't changed since the beginning. And just as I showed you in that graph, this one right here, this is the last
Yeah, that's incredibly consistent.
10 years, and it's within, it's an 8.17 kilowatt total system, and it produces pretty much within 200 kilowatt hours per year of 8,000 kilowatt hours.
Yeah,
We
that's
did have one
incredible.
good year in 2015. We got 8,500 kilowatt hours. So the answer is I haven't been able to discern any change in performance since the system was installed and completed with all the modules, you know, over 10 years ago.
Very interesting.
Yeah.
Yeah, maybe this is good data to support that panel degradation is not a real significant issue.
It's not in the initial years, you know, they were saying X% per year. And then they started modifying those estimates downward because they were being too conservative about it.
Right.
So, yeah, we're happy with this consistent performance. And our house uses about 8,000 kilowatt hours per year. And except for the electric car,
Mm-hmm.
that adds a couple thousand per year, but then we get 8,000 miles of driving in addition. So,
Yeah. Just got a question in the chat about radiant floors. Have you ever thought about doing radiant floor in your house to maybe be able to use the low temperature heat more effectively?
I think in the early years, as we were planning our house in 2007 and 2008, we considered all those options, but realized that we have ductless mini split heat pumps that heat and cool our entire nearly 3,000 square foot house. And you know, given the cost of the systems and how much it would have been to put a radiant floor in and have to fuss with, I guess, water and
Glycol and
whatever
pipes.
glycol flowing through the floor. This system is much cleaner. I mean, we don't even have a ductwork system through the whole house. It just, we have 3 ductless mini split heads in the house that serve 3 zones of the house. And so we can heat and cool our zones all separately from one another. But no, I think we ruled out the radiant floor idea.
Sure. So there's research that has been done on what's called high thermal mass heating systems versus low thermal mass heating systems, and which one is better for very high efficiency homes like your LEED Platinum house. And the answer is that with very high efficiency homes, you really don't want a high thermal mass heating system, such as a glycol or water-based radiant floor system. You want a low thermal mass system, such as ductless heat pumps or some sort of air source heat pump ducted system, where as soon as, you know, the sun comes around and hits those windows, it can shut off the heat and then not continue to radiate heat and then overheat the house. So that's been the general consensus.
Thanks. You reinforced my good decision years ago.
Yeah.
Yeah.
All right, well, let's maybe move forward to some of the slides. I want to plug the next events. So the next Green Energy Series is really cool. It's one that is the founder of Seeds for the Soul, which is a peer-to-peer loan program. She's going to present on how that loan program works and how it's successfully been a another kind of way to help make solar more affordable. As Doug mentioned, like solar systems in 2009 were really expensive, and today they're quite a bit more affordable, but for many people, being able to write a check for $20,000 upfront is still, you know, a burden that cannot be overcome. So these peer-to-peer loans can really help folks who don't have $20,000 in savings be able to come up with the upfront cost for a solar system. So really looking forward to this webinar. Please mark your calendar. Go to the next slide. On August 7th, we also have a solar social event that's over in a building called Place to Be. It's at 1661 Southeast 3rd Avenue. So you want to hang out with other solar aficionados and nerd out about solar, or just, you know, get some social, then yes, please mark your calendar for August 7th, 5:30 to 7. All right. Well, any last ending questions? I don't have any more questions. Well, thank you so much, Doug. This was a great presentation. I personally look forward to visiting your house and installing a heat pump water heater for you. So you can get your last appliance off of gas and then kill the meter.
Alrighty,
So,
it's been fun.
okay, thank you so much. Take
All right,
care.
thank